You ever just stop and think about how we translate the world around us, like the heat from your coffee or how tall that building is, into the actual language of science? Well, today, we're going to dig into the very foundation of physics, how we go from just seeing the universe to precisely measuring it.
So how do we do it? I mean, this is the fundamental leap that all of science is built on. It's one thing to say, hey, that's a tall tree, right? That's subjective. But how do we turn that feeling into a hard fact that a scientist on the other side of the world can check and get the exact same result? That's the big puzzle we're going to solve today.
Okay, so it all kicks off with a really simple but super important distinction. There are two ways we observe things. On one hand, you've got your senses. The sky is blue, a rock feels rough, coffee smells amazing. That's all qualitative. It's how we experience the world, but it's not really science. For that, you need the other side, the quantitative stuff. We don't just say a flagpole is tall. Nope, we say it's 10 meters tall. We don't say a rock is heavy, we say its mass is 2 kilograms. See the difference? It's all about the numbers.
All right, so here's our game plan for today. First up, we're going to really lock down that difference between seeing and measuring. Then, believe it or not, we'll get into the art of a good guess. After that, we'll dive into the actual language of science. And to wrap it all up, we'll see how to build some seriously complex ideas using just a few basic building blocks.
Okay, let's jump into part one, moving from just a casual glance to a solid, numbered fact. Look, our senses are amazing, but physics is all about experiments. And here's the key. For an experiment to mean anything, someone else, anywhere in the world, has to be able to do it again and get the same results. And that's just not going to happen if your notes say something was kinda hot or moving pretty fast. You've got to have numbers.
And that brings us to what a real scientific measurement actually is. It has two parts, and you absolutely cannot have one without the other, a number and a unit. If I tell you a door is too high, what does that even mean? 2 feet, 2 inches? It's totally useless. But if I say it's 2 times meters, now we're talking, that's real data. It's specific, anyone can check it, and that right there is the foundation of all physics.
All right, but let's be real. You don't always have a fancy measuring tape or a scale in your pocket, right? Sometimes you just need a quick, kind of back-of-the-napkin answer. And that brings us to a skill that is way more important in science than you might think. The art of the educated guess, or as we call it, estimation.
Now, estimation isn't just, making stuff up. It's a genuine skill where you use your experience and a bit of logic to get an answer that's good enough for the situation. You do this all the time. It's that quick calculation you do in your head to figure out, do I have enough gas to get home? Or the classic, how many pizzas should we order for this party? That's estimation in action.
And there are basically two main strategies to get good at this. First, you can take a big, scary, unknown thing and break it down into smaller pieces that you can wrap your head around. Like, want to estimate how tall a building is? Well, you can probably guess the height of one floor, right? So you just count the floors and multiply. Or you can do the opposite. You take something really small, like the thickness of a single sheet of paper, and then scale it up to figure out the thickness of a whole book.
So yeah, estimation is fantastic for stuff we can kind of see and touch. But physics plays in a much, much bigger sandbox. I mean, how on earth would you estimate the weight of a single electron, or the distance to the Andromeda galaxy? When you get to the wild extremes of the universe, both super big and super small, a good guess just isn't going to cut it. We need a real system.
And just get a load of the scales we're talking about. Physics has to deal with everything from the mind-bogglingly tiny proton all the way up to the edge of the entire observable universe. That is a crazy range. We're talking a difference of over 40 powers of 10. To handle that, we can't have one person measuring in feet and another in some other unit. It would be chaos. We need one single, consistent, universal standard.
And that leads us to the absolutely brilliant solution that scientists all over the world came up with: a shared universal language for science. This is where we get the internationally agreed upon system, the SI base units.
Think of it this way. It's just an agreement, so we can all avoid confusion. Everyone on the planet agrees that a meter means the exact same thing whether you're in Tokyo or Toronto. A second ticks by at the same rate in Cairo as it does in California. This simple agreement is what lets scientists trust each other's work and build on it without any mix-ups.
And this is where it gets really, really cool. It turns out, with just a handful of these basic fundamental units, one for length, one for mass, one for time, and just a couple more, we can describe pretty much everything. They are, as the slide says, the literal building blocks for all other physical quantities.
Okay, so if we've got our building blocks, what can we build? Let's get to the fun part. In this last section, we're going to see the real magic of this system by building more complex measurements, what we call derived units, from these super simple starting points.
And a derived unit is pretty much exactly what it sounds like. It's not one of the basic bricks. It's the cool spaceship or castle you build with the bricks, usually by multiplying or dividing the base units.
Let's try one. How about something common but also kind of abstract, like force? What's the unit for force? Well, if you look at our list of base units, there isn't one. But that's okay, because we can build it. So we start with a recipe, a famous one. Force equals mass times acceleration, okay? Easy enough. We know the base unit for mass, that's the kilogram. Now, acceleration is a little trickier. It's how fast your speed is changing, so it's measured in meters per second every second. Or, to make it cleaner, meters per second squared. So now we just plug our base units into the formula. We get kilogram times meters divided by seconds squared.
And here's the punchline. That whole mouthful, kilogram meter per second squared, is a bit clunky, right? So scientists gave it its own special, much cooler name, the Newton. We just took our basic building blocks and built a brand new unit to describe something as complex as force. How cool is that?
And this amazing idea doesn't just stop with force. Oh no. This same principle applies to tons of other really important concepts in physics.
I mean, just look at this. The joule, which we use for energy, it's just kilograms, meters, and seconds all mixed together. The watt, for power, same ingredients, just a slightly different recipe. Pressure, electric charge, you name it. They're all just clever combinations of the same few simple base units. It's this beautiful, elegant system that lets us describe the whole complex universe.
So think about the journey we just took. We went from just looking at something to making an educated guess all the way to a universal language that lets us build these huge, complex ideas from the simplest possible parts. It really makes you wonder, doesn't it? Now that we have this incredibly powerful language, what other secrets of the universe are just waiting out there for us to measure, to describe, and finally, to understand?